We're now going to shift into something more theoretical involving orbitals. We're going to begin to look at how do orbitals work for these complicated, large, delocalized pi systems. In order to do that, I'm going to give a very, very brief review of how we looked at pi orbitals in just when they were by themselves. We discussed this all the way back in Chapter 2. How do we make double bonds? What we saw in that chapter is that we could sort of separate the orbital theory of how single bonds are made from the orbital theory of how double bonds are made. Single bonds were made using the valence bond, where we just found individual sp hybrid orbitals, sp, sp2, sp3. We imagined having one electron in each orbital. We overlapped those. That formed a sigma bond. With pi bonds, what we said was we could actually use sort of a molecular orbital theory for doing pi bonds. In the molecular orbital theory, you overlap the orbitals while they're empty. You do mathematical calculations that creates new orbitals. In other words, new shapes for the electron clouds, and also new potential energies for these new electron cloud shapes. When we overlapped them, we always overlapped them in phase, where positive signed parts of the orbital overlapped with positive signed parts. And then we overlapped them out of phase, where positive sign parts overlapped with negative sign parts, not charges but just mathematical signs. They would cancel out in the middle, and because the resulting orbital would be smaller, would have a higher density, there would be more repulsion, its energy would go up. For the in-phase orbital, because the orbital would be larger, the electrons would have a larger space to spread out in, and generally we saw the potential energy goes down. So we would first make a diagram like this, where we started with two individual p orbitals at what we called the zero energy level. We imagined them overlapping in phase, creating a pi bonding orbital, and then out of phase, creating a pi anti-bonding orbital. And the energies of these two orbitals would be gone. We would now have two different orbitals, and they would have different energies. As you'll see later, we then filled those in with electrons to get a final picture of how the electrons were shifting around to make the bonds. So there are several things I want to just sort of summarize about this. First of all, you'll notice that in that pi molecular orbital bonding picture, we had the same number of molecular orbitals, pi orbitals in this case, as we started with p orbitals. And that was required because each orbital can hold a pair of electrons, and if we destroy an orbital, but we still had electrons, there would be no place for those electrons to go. The other thing is that if we look at the diagram, and I'll show you this again, we have about the same number of anti-bonding orbitals as we have bonding orbitals. In this case, the pi's and the pi stars. So that's going to be important. And furthermore, they're sort of arranged around this middle energy level, the zero energy, where the p orbitals by themselves started. Adding on to this, if we look at all of the orbital energies in a molecule like ethylene, which is CH2 double bond CH2, we see that we have sigma and sigma star, sigma bonding, sigma anti-bonding orbitals. However, the energy changes for the sigma orbitals are much larger than the energy changes from the pi orbitals. So if we assume all the orbitals started kind of right on this middle dotted line, a little bit above or a little bit below, but close to that, we see that the sigma orbitals, the bonding ones went way down in potential energy, and the anti-bonding ones went way up in potential energy. The pi orbitals, in contrast, move down relatively just a little or up relatively just a little. In most molecules, when we fill these in, it turns out we'll probably end up with just about the right number of electrons to fill all the way up to the original line, with little or few or no electrons above the original line in antibonding orbitals. Therefore, what we see is right at this line, we're going to have a change in our orbital diagram. We're going to have one orbital at a certain potential energy that will be completely filled, and it will be the highest energy occupied molecular orbital. Then directly above it, it could be far away, but it's still above it, the next orbital in energy will be the lowest energy unoccupied or empty molecular orbital. These orbitals have special significance, and they have been given actually special designations. The highest energy occupied molecular orbital is abbreviated the Homo, H-O-M-O. The lowest energy unoccupied molecular orbital is abbreviated the Lumo. Together, they are called the frontier orbitals of the molecule, since they lie right on the border or frontier between occupied and unoccupied orbitals. Many years ago, a Japanese theoretical chemist named Fukui came up with a theory of reactivity called the frontier molecular orbital theory. He theorized that most reactions occur between a HOMO of one molecule and a LUMO orbital of another, since bonds are formed by combining orbitals, and you have to have exactly 2 electrons when you make a new bond. The HOMO of one would supply the 2 electrons, the LUMO of the other would supply the rest of the orbital, but it couldn't be filled, or else that would be a net antibonding reaction. So we basically consider that almost all chemistry occurs in the frontier orbitals. So now let's look at how this pi orbital picture would work when we have to make a pi orbital from 3 p orbitals. So if we compare the resonance structures of the allylic carbocation, we can see that the double bond is located between different carbon atoms in the 2 resonance structures. So for example, it's located between the left 2 carbon atoms in the first structure and between the right-hand carbon atoms. Furthermore, what we see is there will be a carbocation which represents an empty p orbital on the 3rd carbon. When we first looked at resonance, we talked about how the real molecule would be a hybrid of these 2 structures, and we tried to kind of draw, in a Lewis structure sense, what the hybrid would look like. The problem being that because the Lewis rules are very strict, you couldn't really draw a hybrid accurately with Lewis structure rules. Because, for example, in this thing we would say 50% of the time, more or less, there would be a double bond on the left 2 carbons. So in other words, like half of a double bond. So we draw that in with a dotted line. Then 50% of the time, we would have double bond on the right-hand 2 carbons, so another half of a double bond. But then that middle carbon has too many electrons around it. We would also say that about 50% of the time, there would be a charge on one end. The other 50% of the time, there would be a charge on the other end. So again, we don't have full 100% positive charges on each end. We have partial positive on one end and simultaneously a partial positive on the other. What this hybrid really suggests then is that the carbocation, the allylic carbocation, really doesn't contain 2 partial double bonds. What it contains is 1 pi bond. that actually goes over all three atoms simultaneously by overlapping the individual p orbitals. We call this a delocalized pi system. It exists because what we're looking at then is an orbital that doesn't just put two electrons between two atoms to make a covalent bond. That was the assumption that Lewis made. All covalent bonds would be made by two electrons shared between two atoms. Instead, what we have is two electrons that are shared in a cloud over three or even potentially more atoms, three in this case. So that would create an orbital structure that would look like this: p orbital overlapping with p orbital overlapping with p orbital. Now, to properly make this orbital then, what we would have to do actually is make bonding and antibonding orbitals. Because it's three p orbitals, we can't just have one delocalized orbital. The three p orbitals by themselves could each hold two electrons for a total of 6. Just having one delocalized orbital would only hold 2 electrons, so where would the other 4 electrons go? So here is the molecular orbital picture of an allylic pi system. Like, for example, an allylic carbocation, but not limited to carbocations, as we're going to see. What we see is that originally all of the p orbitals, before we made molecular orbital atom, they would have what we call a zero energy. They would just be right here all lined up. I kind of have these 3 lines showing that. Then we start overlapping them. But it turns out that there's rules about how you can overlap orbitals to make a molecular orbital. One of the rules is that you have to overlap them either in phase or out of phase. The other rule, which we haven't talked about, is that in these pi systems, they have to have a certain symmetry to them. The two ends have to basically be kind of similar. The only thing that can be different is the colors, or in other words, the signs of the orbitals. And so we can either be symmetric, where the two ends end up being identical signs. So we have a positive sign here, we also have a positive sign there. Or they can be anti-symmetric. That's not asymmetric. So asymmetry means you have no symmetry at all. Anti-symmetry means that you have a symmetry, but that the ends are opposite to each other. So a positive orbital here reflects across the middle of the molecule onto a negative orbital there. So putting those things together, 1, we need to make 3 orbitals. 2, we can only overlap them in phase and out of phase. 3, they have to either make symmetric or anti-symmetric orbitals. We get something like this. There are 2 other features of this. When we overlap orbitals, and the overlapped orbitals change sign. So for example, here we're going positive to positive to positive, but here we're going positive to negative to positive. In the space between a positive and a negative overlapped orbital, we create an area where the orbitals cancel out, meaning that there is 0 electron density. We call those areas nodes. You can recognize where nodes exist just by looking where it's white, so it's positive, then it's black, so it's negative, then it's white, so it's positive or shaded, okay? What we see is that the lowest energy molecular orbital is almost always going to have 0 nodes. All of the orbitals will overlap in phase. It will also be symmetric. So we start with our first one being in phase and symmetric. The second one, or the one next above it, will have 1 additional node. So since it's 0, we add 1. This one has 1 node. It will also be anti-symmetric. Putting those two things together, what we get for our second orbital is an orbital like this, where we have cloud on one end, cloud on the other, but we have a node in the exact middle. And the two clouds, they come from orbitals of opposite mathematical sign. Going up again, then we would have two nodes. It would be symmetric. Well, to have two nodes between three orbitals, that means we have to change phase every time there's an overlap. So this is the orbital where all of the orbitals are out of phase. You can see the two nodes. You can also see that it is again symmetric because on one end above we have a positive sign for our mathematical orbital, and on the other end we have a positive sign. So this is our allylic pi system. These three orbitals with these three energies, we can then take the electrons and put them into these. Now, this then explains the concept of delocalization, because when we do reactions, we react with an individual orbital. So you can see that this orbital, for example, has this pi cloud that goes over all three carbons. And so that's how we can represent it as just one thing, even though it's kind of built out of, in Lewis structure terms, something with a double bond on the left and a double bond on the right. When we put it in molecular orbitals, it all coalesces into one thing. So delocalized pi orbitals essentially explain resonance. And if you have resonance, that means you have delocalized pi orbitals. And if you have delocalized pi orbitals, it means you have resonance structures. So these orbitals are summarized below in words similar to what I used above. Now, when we look at the allylic pi orbitals, those are just empty orbitals. Remember that in our molecular orbital theory, what we would do is we would first make orbitals. Then, once we had orbitals, we would take all the electrons we had and fill them into the orbitals, starting at the bottom until we ran out of electrons. And when you first learned it, you either use circles or boxes, and you put these little arrows in, and the arrows pointed in opposite directions, and that was important. That was the spin of the electrons, right? But you could only put two in a box. They were always in opposite directions. Most organic chemists, or say advanced chemists, throw away the boxes, and they just use lines, which represent the orbital, but they represent the potential energy of that orbital. And then we just draw the arrows through the line. In terms of counting electrons, what we have to do is we have to look at one of the resonance structures. It really doesn't matter which one. All of the resonance structures should give the same answer. What we want to do is look at just counting how many electrons are in the overlapped pi bonds, or in a free radical, if that's part of the system, or in a lone pair, if that's part of the system. And if there's a carbocation, that's contributing a pi orbital, but 0 electrons. So when we look, for example, at the allylic cation, we can see here's our double bond that's part of our pi system, and it has 2 electrons in it. But then we have the carbocation, and it has 0 electrons. So we have a total of just 2 pi electrons in our delocalized resonance structure sort of described pi system. So then when we go to our pi orbitals, we can see that we would fill those into our lowest level, our lowest potential energy pi orbital, which looks like this, where all 3 orbitals are lined up, overlapping in phase, creating one big cloud of pi electrons. So we would have a nice big delocalized cloud of electrons. We would then, above it, have our first empty orbital. So the highest energy occupied one would be this. Then we would have the first empty orbital, the Lumo, and that Lumo looks like this. And the interesting thing about that LUMO is that there's no orbital density in the middle. So if something wants to come and react with the LUMO, it can only react on the two ends. But if we make the assumption that the two ends, that the clouds are the same size, it should be equally able to react with one end or the other. And that explains how, if we take a nucleophile, which has a filled orbital, so we're going to use its HOMO, and we react it with the allylic cation, which has an empty orbital, so we're going to use a LUMO, it could react 50% of the time on one end or 50% of the time on the other end. When we look at radicals, what we see is that we have 2 pi electrons for the double bond plus 1 electron for the unpaired electron of the radical. When we fill them in, 1, 2, and then 1 here in the middle. So after the frontier molecular orbital theory was proposed, people started adding radicals to it. We have a name for this. This is the singly occupied molecular orbital. In free radical chemistry, we have reaction between a HOMO and a SOMO, or 2 SOMOs. It depends on what's happening. Okay? So when we look here then, what we can see is that, again, the radical, in other words, the unpaired electron, it's making an electron cloud that's 50% on one end and 50% on the other, but nothing in the middle. So that means the radical could reach out with this end and grab an atom, or could reach out with that end and grab the atom. And that's why in our intermediate, which had resonance, we could react on either end. Finally then, we'll look at anions later, but anions would have 2 electrons for the pi bond, 2 electrons for the lone pair. They would fill up to here, and in this case we would see that the highest occupied molecular orbital would be this middle orbital, not the one on the bottom. And again, we would see that anions should react 50% on one end, 50% on another. Since anions are going to react like nucleophiles, they're going to use a filled orbital. So these words basically again explain the frontier molecular orbital theory. Again, it's an explanation for why we have chemical reactions, and we say that essentially when we have a reaction between 2 species, one will be donating electrons from a filled orbital, its HOMO, into a low energy unoccupied orbital. And so this would be an example of how the frontier molecular orbital theory would describe an SN1 reaction, the second step between the carbocation and the nucleophile, in this case a chloride ion. What the frontier molecular orbital theory would say is that the carbocation has a LUMO, which is an empty p orbital. Since these are all sigma bonds, their potential energies will all be much lower, but the empty p orbital will be higher energy, and it will be empty. The nucleophile is going to use a pair of electrons. So those electrons have to be located in an orbital, so it's therefore going to use one of its HOMOs in order to make the bond. The bond is then formed when the LUMO of the carbocation and the HOMO of the nucleophile overlap in this direction. We get this HOMO-LUMO interaction. The pair of electrons flows into a cloud that then goes over the entire space. The orbitals change shape because of repulsion, and we get a final orbital that looks like this. It was made from these 2 orbitals. These 2 orbitals are now effectively gone, but they've been replaced by this orbital plus an antibonding orbital that we normally don't draw. And there's 2 electrons in it. So if we do the same thing with an allylic carbocation, as I mentioned, we can see that the allylic carbocation, the LUMO, is going to have empty orbital on one end, empty orbital on the other. And so therefore, the nucleophile could either overlap this way or could overlap that way. And that's going to create 2 different regioisomeric products.